Hello everybody. Let's take a look at some early experiments that helped us determine atomic structure. And so I'm going to try to keep this pretty short because what I really want you to do is to watch some animations that I posted in Sapling. So the first animation I'd like you to watch is Thompson's cathode ray tube experiment. So watch that first and then come back and watch this video. And what's really cool about this is actually a picture of Thompson in his lab, and you can actually see the cathode ray tube there on his workbench. That's pretty neat. So we have a picture from probably the late 1800s of J.J. Thompson running his cathode ray tube experiment. So let's talk a little bit about what he did. So let's first discuss what a cathode ray tube is. And so this is an evacuated tube. I think it was down to maybe 10 to the minus 6 minus 7th millimeters mercury back then. They can make them better now. You have two pieces of metal on each end. You pass a high voltage between those. And the negative end of that circuit, turns out there's a beam that comes across from that. Okay, so it comes from the cathode, hence they're called cathode rays. Now you can't see these things, but when they first did it, you could kind of see a tiny flash when it hit the end of the glass. And then they added some phosphorescent material at the end here so they could see it better. And then they started coating the whole inside with a phosphorescent material that would light up. So you could then see these cathode rays. Okay, and here's an actual real cathode ray tube here, or CRT, we can call it CRT for short. You may or may not have heard the term CRT. Back when I first started teaching chemistry, I used to always say, oh, this cathode ray tube was the forerunner of the modern television. Well, televisions have changed. We use liquid crystal displays, plasmas, all sorts of different things now. We don't have these big picture tube TVs, but those were cathode ray tubes, and even computer monitors were cathode ray tubes. Now they're not. But anyway, so here's this beam of electrons coming across that cathode ray tube. Now let's talk about so Thompson didn't invent the cathode ray tube. That was invented before him. But what he did, what's really cool about scientists is they try different things. And so what he did is he said, well, what if I bring a magnet up to the cathode ray tube? And you can see that the beam here is deflected by that magnet. He also said, let me keep scrolling down, I don't mean to go too fast here, but I don't want to take too much of your time. He also tried an applied electric field, and that would also bend the beam as well. So that's pretty cool. So this is showing, this figure here is showing the electric field and then also the magnetic field. And he could deflect that beam. So normally the cathode rays are going to go straight through the tube. But bring in an electric field, they deflect toward they're attracted toward the positive pole of the electric field, deflected away from the negative pole. So that should tell us what charge they are. And you could also do the same thing with a magnetic field. Now the really cool thing, and I hope you can read this text okay, the really cool part of his experiment was that he adjusted his electric field so that the deflection was the same, so this deflection angle here was the same as the magnetic field. And then using some equations based on the field strength of the magnetic field, the electric field, the length that the beam traveled, and I think it talks about this in the animation. I'm not going to go into all the details here, but based on this experiment, he was actually able to determine, oops, that's the next guy, let's not put him up yet. The charge, let's just write charge, I was going to put electron, but let's say charge, so that's a C there, I apologize. Charge to mass ratio of these things. And Thompson concluded, and he kind of made a little bit of a leap here, because a lot of scientists didn't believe him, but he knew they were negatively charged because they were attracted to the positive pole of the electric field, repelled by the negative pole, so they were negatively charged. And what he did, another part of the experiment, he tried 20 different metals. And guess what? Every single metal he tried emitted these cathode rays. So his conclusion was that these charged particles were a fundamental part of all matter. Okay? And some scientists, there's even a quote from someone at a conference where Thompson presented this work very early after he had done it, and the guy said, "I thought you were pulling our legs." No, a lot of scientists didn't believe that there were these negatively charged particles that were fundamental to all matter. So anyway, what I want you to focus on, I kind of want you to know the experimental setup, because this experimental setup is pretty neat. This is a pretty sophisticated experiment for the late 1800s. But the most important thing I want you to know is the important discoveries. And one was the charge to mass ratio of an electron. And yes, we now know these negatively charged particles as electrons. Okay, and he determined he didn't quite get this value. His value was pretty close to this from his first experiment. This value got revised over the years as experiments got better, but negative 1.76. Remember, electrons are negatively charged. Coulombs per gram. Now, coulombs is the SI unit of charge, so don't worry about that too much. So there it is, charge to mass ratio of an electron, and he essentially, although it was known that there was something negative that came out of some atoms, but he was the first one to say, okay, there's these negatively charged particles, let's call them electrons, and they're fundamental to all matter. Okay, so essentially we'll say he discovered electrons, and he determined their charge to mass ratio. Those are kind of our two big things from the cathode ray tube experiment. Discovery of electrons, charge to mass ratio. Now, let's go to the next guy. This is considered one of, I think it was in, I forget what physics magazine, but the readers of a physics magazine voted this next experiment as one of the 10 best experiments ever. 10 best ever. Okay, so we learned a lot from the cathode ray tube experiment. Make sure you know that one. Let's scroll down to the next handsome gentleman, Robert Milliken. And so go and watch the next animation and then come back, pause the video. There should be another animation in Sapling called Milliken's oil drop experiment. So take a look at that, watch that, then come back. I'll highlight some things from that experiment for you. So here's a really cool picture. Again, this is, oh boy, when was this? So, it's early 1900s now. I think we've moved out of the 1800s into the early 1900s for Milliken's oil drop experiment. But this is his apparatus. And so this big clunky metal thing is so that it can be an evacuated chamber, low vacuum in there. Here's the, microscope or telescope, however we want to say it, to look inside the chamber. This is what's called the atomizer. This is to spray fine oil drops, so spray mist of oil into the chamber. Spray mist of oil into the chamber. Yes, I can. Oh well, live recordings. Here we go. So spray a mist of oil into the chamber, and then he could view what would happen to the oil drops. Here's where he could adjust the electric field. Okay, so this might not look like much, but heck, this is pretty sophisticated for 1900. Pretty cool stuff. And this is supposed to give you a scale. I can't see that, and obviously in the recording it's going to be worse than in my picture. That doesn't quite look like a yardstick. It looks like it, I don't know, maybe it goes up to about 20 inches or something, but it's not a particularly big apparatus. Okay, so let's talk about the results of the experiment. So here's just a figure to show kind of a cutaway view. Remember, this is an evacuated chamber, low vacuum chamber. Here's your atomizer. Spray a fine mist of oil drops. They would fall through, so he had a small hole in this top floor right there, so only a few would fall through at any given time. Okay, so he could isolate oil drops coming through. The first thing he did is he looked at the terminal velocity of those oil drops, and he was able to determine the mass of an oil drop. Okay, because that's going to be very important in just a second. So that's the first thing he did. Next thing he did with the experiment is then, as the drops are coming down, he hits the remaining air. Now again, these are evacuated, but there's still some air inside this chamber. He hits the air molecules in there with X-rays. And X-rays are high energy electromagnetic radiation. So what do those do to those air molecules? It knocks electrons off of them. Okay? It knocks electrons off those air molecules. So I'm going to write E negative. So now there's all these negative electrons. So it's knocked these electrons off the air molecules, and these electrons then adhere to those oil droplets. So those oil droplets now have a negative charge. So then the cool thing is he can adjust his electric field, positive plate up here, and he can actually draw the oil drops back up, depending on how strong an electric field he applies. And if he did it just right, oh God, I did this in the last recording. If he did it just right, he could suspend an oil droplet. And that's really cool. He could suspend it and then look at the forces on that oil droplet. And we'll go to the next slide and look at what those forces were. The animation talks about this as well. Okay, so here are all the forces. Here's the applied electric field. Gosh, I must be hitting it with my hand. Sorry about that. I shouldn't get frustrated. So there's the applied electric field. So he could adjust that until he suspended that oil drop, right? Here is the charge on the drop. Okay, doesn't know what that is. He's actually going to solve for that. Okay, but he knows the mass. He measured the mass of the particle, the oil drop, and this is the force due to gravity. All right, which is known, obviously. So he knows the mass of the drop. Check. He knows the force due to gravity. Check. He knows what electric field he applies. This force pulling the drop up is equal and opposite to the force pulling the drop down if it's suspended. Sets those things equal to each other and solves for the charge of the drop. Pretty cool stuff. And what he found was the charges did vary. Okay, but they were all a multiple of a smaller number, and that number was about negative 1.6 times 10 to the negative 19th coulombs. Okay, incredibly small charge. I mean, it's something that, you know, without this sophisticated type of experiment, and again, early 1900s, sophisticated, you know, I think even by today's standards, but he was able to measure a very small charge. So the charge of a single electron, as you might expect, is really tiny. Okay, so that's the charge of a single electron. And we know this charge a little bit better. He wasn't quite spot on, but he was really close. We know it even to more sig figs than that now. So then, so not only did he actually determine the numerical charge, so that's one thing you should know that Milliken figured out, numerical charge of electron. Okay, make sure you notice that's different than Thompson. Thompson just figured out that they were negatively charged. Milliken came up with the number, the numerical charge. Okay, so that's one thing you should know about the Milliken oil drop experiment. The other thing was that using this charge, okay, I dropped my negative sign, but the negative sign is still there. And the charge to mass ratio, it was the charge per 1 gram, so 1 gram, and it was negative 1.76 times 10 to the 8th coulombs per gram. And let me get my calculator here. I should know the mass of electron. I think it's 9.11 times 10 to the negative 28th grams, but let me just double check. Okay, this comes out to 9.1. So the numbers that we have here, 9.1 times 10 to the negative 28th grams. Look at that mass. Look how incredibly small that is. Could we weigh that out on a balance? No, heck no. But knowing the charge to mass ratio from Thompson's experiment, now the numerical charge that Milliken figured out, he took those two pieces of information and calculated the mass. Oh my gosh. I'm having all sorts of trouble. I'm putting my hands on the bottom of my screen here. Sorry about that. He determined the mass of the electron. So that's the second thing you should know. So pretty cool stuff. Numerical charge of an electron and the mass of an electron. All right? I hope you think it's cool, and particularly, think of the time frame. We're looking at, 110 years ago. Really sophisticated experiment. Okay, so what I want you to try to do is appreciate science too. I mean, there's a lot of cool stuff that goes on in science. And you're probably going, but yeah, we know about protons and neutrons and electrons and all that stuff. But, science is about discovery, and this was a big deal back then. Big deal, and I think it's still pretty darn cool. Okay, so where do we go from those two experiments? Well, Thompson comes back and says, I'm going to propose a model of the atom. And this model, or this representation of Thompson's model, is affectionately known as the plum pudding model. He was an English physicist, and I've never had plum pudding, but plum pudding has raisins in it. And so he said, we have this diffuse, let's say cloud, so it's spread out of positive charge. Okay, so they knew there were electrons, so they're negative. So there had to be a counterbalancing positive charge because atoms are neutral. Okay, so he says there's this diffuse spread out positive charge, and embedded, like raisins in plum pudding, are these negative electrons. Okay, so that was Thompson's model of the atom, the plum pudding model. All right. So that was kind of the first real model of the atom that was proposed. And again, we're still looking early 1900s. Okay, there's the name, plum pudding model. You got it. Okay, now, here comes another guy, Rutherford, Ernest Rutherford. Every time I see this picture, I have a friend who teaches high school chemistry who looks a lot like Rutherford. And when I found this, because I had always seen these old pictures of Rutherford, when I found this younger looking picture of Rutherford, that looks like my friend Steve. So I sent my friend Steve an email and I said, hey, I found this picture, take a look at it. You look like Rutherford. And he says his high school students tell him that all the time. So I wasn't wrong. Okay, enough of that. So Rutherford comes along, and Rutherford had actually, he was a graduate student that worked for Thompson. So he had studied physics, and he was actually a chemist too. He had a degree in chemistry and physics, and he worked with Thompson. Okay, so he comes along, and he had done some work with this new discovery of radioactive particles. So he starts thinking, can I use these to probe atomic structure? Can I use, in this case, alpha particles? And an alpha particle is the same as a helium nucleus. It has 2 protons and 2 neutrons. So we're going to talk, we haven't yet talked about atomic number and mass number, but 2 protons, 2 neutrons, that's an alpha particle. So it's a positively charged particle. So he starts thinking, well, what happens if I start bombarding things with these particles, these new radioactive particles? So what he takes is a very thin piece of gold foil, and I mean very thin. We're talking about 400 nanometers thick. Okay, do you remember what nano is? 10 to the minus 9th meters. Okay, so really, really thin piece of gold foil. And he takes a radioactive source, aims this beam of alpha particles at the gold foil, and if Thompson's model was correct, this plum pudding model, he expected pretty much every alpha particle to go straight through with essentially no deflection. They should have just ripped right through that diffuse sphere of positive charge. That was what he expected, and in a way he believed in Thompson's model. Okay? And he wanted to prove that it was right. Now, here's the really cool thing about this experiment. Let me show you the actual apparatus. Now, this has been cut away. This is actually in, I believe, a museum at the University of Manchester in England, where Rutherford spent quite a bit of his years doing research. But you can see the pieces. There's the alpha particle source over here. Here's the gold foil. Here's the microscope that Rutherford probably is not spending much time looking through, but he had two students, one an undergraduate, last name was Marsden. His doctoral student was named Geiger, and I bet you've heard that name Geiger because Hans Geiger actually ended up inventing the Geiger counter. Remember, they're working with radioactive substances, so the Geiger counter actually counts the number of radioactive particles coming off of a radioactive source. So anyway, pretty cool shot of his experimental setup. Notice that the screen is coated with zinc sulfide. That's a phosphorescent material, so when it got hit by an alpha particle, it would light up. So think about the poor student sitting there, right? And I'm talking with my hands right now, so you can see me talking with my hands, right? So I'm talking with my hands, and these students are looking through this microscope. 7,999 particles would go through with little or no deflection. The average deflection was less than a degree. I believe in the paper I read it was 0.87 degrees was the average deflection. 7,999 particles pretty much went straight through. Some deflection, but the deflection was averaged to be pretty darn small. And guess what? 1 out of 8,000 particles, alpha particles, deflected at an angle larger than 90 degrees. 1 in 8,000 alpha particles. Okay, deflected at greater than 90 degrees. That might not seem like much, but to Rutherford that said the plum pudding model could not be correct. Every alpha particle should have just ripped through that diffuse charge. But instead, 1 in 8,000 bounced off at a large angle. So what could that mean? Well, to Rutherford, that meant a new model of the atom. A new model of the atom. And what we'll call the nuclear model of the atom. Okay? So instead of this diffuse positive charge spread out over the whole atom, Rutherford said the positive charge was concentrated in a small, there's the word, a small nucleus. Okay? Very, very dense nucleus in the atom. Most of the alpha particles, these lines are showing the alpha particles coming through. They wouldn't even come close to the nucleus. Wouldn't even come close. But 1 in 8,000 would either hit it directly or come much closer and be deflected at a large angle. Pretty cool stuff. Now, this is not drawn anywhere to scale in terms of the size of what we call the electron cloud, the region of space where the electrons are moving, and the nucleus. Not anywhere close. Okay? Let me try to paint a picture for you and give you an appreciation for how small the nucleus is relative to the region of space that the electrons occupy. Okay? So, take a helium atom, which is really, really tiny. Okay? It's actually smaller than a hydrogen atom. We'll talk later in the course why that is. But helium is really, really tiny. So take the electron cloud of a single helium atom and in your mind expand that so it's the size of the Earth. Are you with me? So one single helium atom, expand the electron cloud, the region where the electrons are, all the way out to the size of the Earth. All right? The nucleus of that ginormous, yes, ginormous is a word. I don't know, it showed up in the dictionary a few years ago. The ginormous atom, the nucleus, would have a diameter of about 175 meters, okay, which is probably what, about 600 feet, 200 yards. Okay, so we'll work with, so 175 meters, let's say 200 yards. Okay, football field's 100 yards. Okay, the nucleus would fit inside a sports stadium. Okay, it would fit inside a sports stadium. And the electrons would be in a region of space that would take up the entire Earth. You know, wrap your minds around that. I just think that's pretty amazing. Okay, so the nucleus is really, really tiny compared to the volume that's occupied by the electrons. Okay, so that's the nuclear model of the atom. Protons in the nucleus, electrons moving about the nucleus. We'll talk more later in the course about how we envision these electrons moving. Neutrons actually, and you've heard neutrons, actually weren't discovered until 1932. Okay, but they were harder to discover because they're neutral. It's easier to pick up positive particles and negative particles. Okay, I think that's enough for the recording. I think I went longer than I wanted to, about 25 minutes. Plus I have the animations for you. But cool stuff. Try to appreciate the science that went into the discovery of what we take for granted now, protons and electrons in particular. We'll talk in class a little bit about the discovery of neutrons as well. All right, have a great day.